So in this video, we're going to go over quadratic modeling, and the first thing we're going to go over is maximum minimum value of a quadratic function. So what is the minimum value or maximum value of a quadratic function? Well, quadratic function takes on a parabolic shape, right? If a is greater than 0, remember a is one of the coefficients, right? If you're in standard form, a is the coefficient on your quadratic term, okay? Or a is less than 0. If a is greater than 0, your parabola faces up. If a is less than 0, you have a parabola that faces down. And if we really dive into what's going on, the behavior of this shape, okay, as x, okay, increases, okay, as x is really, really negative, your outputs are really positive. And then as x increases, your y values start to go down, they start to go down, they start to go down. Then your y values hit this point, okay, this minimum y coordinate, and then as x continues to increase, all of your outputs keep getting greater and greater and greater and greater and greater, all the way to positive infinity. So this, okay, at the vertex, this is called a minimum value, but it's only the y coordinate, okay? You're only talking about the y coordinate of the vertex, okay? So it hits a minimum y output, and that's called the minimum value of the quadratic. You can only have a minimum value when a is greater than 0, because if a is less than 0, okay, your outputs are growing, 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 hit a maximum, and then as x continues to increase, all of your outputs fall from that maximum value. So the maximum value is the y coordinate of the vertex. Okay? So if you have a quadratic function in which a is greater than 0, you have a minimum value, and you can't have a maximum value because your outputs will go to positive infinity. If a is less than 0, you have a maximum value but no minimum value, because the minimum value, you can't track it because it's going to keep just going down to negative infinity. So when you're talking about maximums and minimums, okay, of the vertex, the x coordinate is when that max or min occurs, and then the y coordinate is the max or min value. So this is important in quadratic modeling because a lot of real-world situations you can create a quadratic model that represents that situation. And take, for example, if we are throwing an object, right, we throw it up in the air and it comes back down, we might want to know the maximum height at which that object reached. Okay, so that's one example of the importance. Okay, a company could come up with a way of figuring out how many things to produce and their costs, and it might look like this type of quadratic right here, and this point right here is going to be how much should be produced so that it makes a minimum cost if the output was cost, okay, and the input was how much to produce, okay. So maximum and minimum value of quadratic function is important. The x coordinate of the vertex is when it will occur, and then the actual maximum or min is the y coordinate of that vertex. Okay, so now let's find, okay, what we'll do is or I should say, let's change that a little bit. Determine if each quadratic has a max or min value, and then we will find that value. So we'll do two problems. Number 1 will be f of x equals negative 3x squared plus 5x plus 1. And number 2 will be f of x equals 3 times x plus 5 squared minus 18. Okay, so in number 1, we see we have a quadratic function. Look at the type. Look at the form of the function. This is in standard form, right? ax squared plus bx plus c. And so remember, you want to know, should this have a max or a min? If it's facing up, that's when a is greater than 0, we have a min. If your quadratic is facing down, that's when a is less than 0, you have a max. So what is a here? A is negative 3, so a is less than 0. So that means we know this quadratic faces down. So this will have a max value. So now we have to find the maximum value. Remember, the maximum value is what is the largest output that this function can produce. So to figure that out, you need to know about the y-coordinate of the vertex. But we can't just get the y-coordinate of the vertex. The first thing we can grab is the x-coordinate of the vertex when we're in standard form, which is negative b over 2a. So that's negative 5 over 2 times negative 3. That's negative 5 over negative 6, so that's 5/6. So then we plug that in. Okay. 5/6 squared, that's going to give us 25 over 36 plus 25 over 6 plus 1. It's going to give us negative 75 over 36 plus 36, I put 35 there, okay, multiply it by 6, so 25 times 6, that is going to be 150, plus 36 over 36, and we get our calculator, and we just find what this value is. So this is going to be negative 75 plus 150 plus 36, we're going to get 111. Okay, 111 over 36. And so this right here is the actual maximum value. The maximum value is 111 over 36. Okay, we don't want to really round that value. We can simplify this a little bit. This is the same as 37 over 12. Okay, so that's the largest output that this function can produce. And number 2, we are not in standard form. Know what form you're in. You are in vertex form. So a sits right outside when you're in true vertex form. So look at the value of a. A here is 3. A is greater than 0. So that means this is going to be a u that faces up, which means this will have a minimum value. Now, if you have vertex form, that means you already know what the vertex is. The vertex here is negative 5, comma, negative 18. So what is the minimum value? Well, the minimum value occurs when x is negative 5, but the minimum value is the y-coordinate of the vertex, which in this case is negative 18. So just know how to get to the y-coordinate of the vertex no matter what form you're in. And know whether or not your quadratic function has a max or min. So I printed out, I didn't print out for you. I attached the application problems that we're going to do. Okay, so if you look at for minimum maximum value, you have a production. So you might want to pause the video, read the problem, and then once you're done reading the problem, play the video. So we have a production problem. It says a financial analyst, determine the cost in thousands of dollars of producing bicycle frames. So he's going to produce bicycle frames, and it's going to output, the number of frames he's going to input, and it's going to output what the cost would be. And it says, here's the first application problem. The function is 0.000025 f squared minus 0.04 f plus 40. So he can input the number of bicycle frames, and it outputs the cost to him. And we could see the value of a is greater than 0, so it looks something like this, okay? And so a says find the number of frames that minimizes the cost. So it doesn't ask for what is the minimum cost, because if we look, the input is f and the output is c. So if I just, drew a coordinate plane, that's not necessarily, think about it, shouldn't really have a negative cost, But I'm just drawing that because I want you to see that F would be the input and C would be the output, okay? And so if we just need to find the number of frames that minimizes the cost and not actually what is the minimum cost, we want the input of the vertex here, okay? We don't want the output of the vertex. We want the input of the vertex. What is the number of frames that should be produced so that it gives you an output that's that minimum cost output? So that would be negative b over 2a, right? Since we're in standard form, we just need the input of the vertex. So that's going to be negative 0.04 over 2 times 0.000025. So that's going to be 0.04 over, and that gives us 0.00005, which gives us 800. So how many bicycle frames should be produced so that this company can have a minimum cost to them? It's going to be 800 bicycle frames. Okay, you might want to write a sentence. 800 bicycle frames will minimize the cost. And then part B says, what is the total cost for the number of frames? So we want to know when F is 800, what is your output going to be? So all we're going to do is plug that in. You can use your calculator. Okay, when you're doing modeling problems, you're probably going to want to use a calculator. So this is going to give us, let's check it out. It's going to give us 24. Now, if you notice, the problem said in thousands of dollars. So the cost when you make 800 is not $24, okay? The cost when producing 800 frames is $24,000. So what that means is, okay, anything, if they make less than 800 frames, if they make more than 800 frames, it's actually going to cost them more than if they were to make 800 frames. That probably has to do with labor, supplies, okay, ordering, manufacturing, all of those things play a role in figuring out the cost to the company to make these frames. Okay, so that's it for min-max. So now let's move on to application number 1 about a water balloon. So if you need to pause the video, read the question, and then play the video. Okay, so the first thing says we need to make a sketch. So let's write down the water balloon. So the water balloon is h equals negative 4.9 t squared plus 27t plus 2.4, okay, and t is in seconds, and h is in meters above the ground, okay. Now, this is an example of what's called a vertical motion model. When you have a vertical motion model, okay, you have something that looks like this. Ax squared plus bx plus c, but okay, these are usually t because what they're talking about is time. But I'm going to just keep them as x's so that you don't get confused with the plus signs, okay? So vertical motion, projectile motion, is anything that takes the shape of, basically that saying that we have in physics, okay, what goes up must come down, and it's going to come down rather symmetrically. It's going to, okay, most vertical motion models, if not all, are going to follow the path of a quadratic. Okay, that's going to be true. Now, most of our models don't take into account air resistance, okay, unless someone's out there actually going and grabbing the data, then you can account for air resistance and so forth. But your constant term, okay, that right there is going to be how high you are off of the ground to begin with, your initial height off the ground. Then we move to our linear term. Our linear term is initial velocity. So whatever the initial velocity of the object is that's being propelled into the air. That's what B is. And A has to do with acceleration. That's going to be the impact gravity has on your object. It's not going to go up forever, right? It's going to go up and it's going to come back down. So this is going to be when you're talking about vertical motion, this is going to be a negative number, okay? So here we go. Now that I've discussed vertical motion model, okay, we can go and do number 1, which says make a sketch of the height of the water balloon after being catapulted. So if we think about this, okay, do we really need, here's quadrant 1. Do we really need quadrant 2, 3, and 4? No, because remember the input is time, right? And the output is height above the ground. So I don't think there is a need for having any negative time, right? Because obviously there is no negative time. And once this water balloon is catapulted, it doesn't say there's any holes in the ground, so we know once it hits the ground again, okay, that it's gonna just hit the ground and the water balloon's gonna pop, okay? So let's think about points that are probably important about this. I would say that the initial time, when time is 0, okay, what is the water balloon's height when the time is 0 above the ground? Another important point is obviously going to be the vertex, okay? So why don't we start by actually getting the vertex here. So if we get the vertex, that's going to be negative 27 over 2 times negative 4.9. Okay, so let's get that value. Now it is okay to round these values. When you are doing these modeling problems, it is okay to be rounding this stuff. So this is going to be 2.756, okay, usually when you round you go whoop. Okay, so that's going to be the time of the vertex. Now remember, this is A is less than 0, so this is going to be a quadratic that goes like this, okay? And so now we need to plug this in and get what the output is. So we have to do negative 4.9 times 2.756 squared plus 27 times 2.756 plus 2.4. So that's going to give us, let's see, it's going to give us 39.594, okay, 39.594. So if you think about it, this vertex, that's the maximum height. So there are 3 pieces that really are important when you're sketching a vertical motion model. It's going to be the vertex, okay, it's going to be the y-intercept, and it's going to be the x-intercepts. Okay, so let's make sure we get all of that. So we got the vertex, so now let's get the y-intercept. The y-intercept is going to be when t is 0, so when your time is 0. And when our time is 0, our height is going to be 2.4. Okay, so our vertex is 2.756, 39.594. Our y-intercept is 0.24. So what this means is at 2.756 seconds, the water balloon is at its maximum height of 39.594. If the water balloon has not been catapulted yet and is sitting there, it is 2.4 feet above the ground. And then x-intercepts, if you're finding your x-intercepts, okay, I'll just put that over here. If you're finding your x-intercepts, okay, you're finding what is the input. Now, if you think about it, x-intercepts, this is t, so these are technically the t-intercepts, okay? So you want to know then what is the input when the output is 0. So if you think about this, the context of the output for this problem is height. So if the height is 0, okay, so that means you're on the ground, okay? When is the water balloon going to be at the ground would be your x-intercepts here. So we're going to have to use the quadratic formula, okay? So that's going to be negative 27 plus or minus the square root of 27 squared minus 4 times negative 4.9 times 2.4 all over 2 times negative 4.9. And so now, let's clean this up. Remember, we clean up that negative 20, this part outside, so that's, negative 27 plus or minus the square root of. Now let's get the value of the discriminant. That's going to give us 776.04 all over negative 9.8. Now for us, okay, these values, if we have to interpret them and put them on the graph, this is very hard to graph these. So we want to round these values. So let's go over making sure we can round these. Okay, so what we do next is first we just round what the square root of 776.04 is. Okay, so that's going to give us negative 27 plus or minus 27.857 all over negative 9.8. So now let's go and get our two x-intercepts. Remember, when you put this in your calculator, this is negative 27 plus 27.857 all over negative 9.8. When you put this in your calculator, you need to make sure you put parentheses around the numerator. Your calculator is extremely smart and follows order of operations. If you wrote this out horizontally instead of as a fraction, okay, you have to remember the numerator is being added before you're dividing by negative 9.8. You get negative 0.087. And then when you do negative 27 minus 27.857 divided by negative 9.8, we get positive 5.598. So this negative one is just going to be all the way over here, okay? We don't really need to graph that. But this, when it's getting to ground, okay, so the second time, our x-intercept is 5, let me clean that up, 5.598. So if we sketch these points, okay, 1, 2, 3, 4, 5, 6, I think I'll go by 5s, 5, 10, 15, 20, oh, I'm going to have to erase this, 25, 30, 35, 40, okay, and this is height above the ground. Okay, so we plot these. And so we've got the y-intercept is 0.24, okay. The vertex is 2.7639, so it's up here. And then 5.5 over here, and then the other one would fall over here. So remember, these are equidistant from the vertex, but there's no point in showing this one because it has no context to the real world situation that we're using this model for. So we don't really need to sketch that. Okay. So there we go. So this is saying, okay, so this is now a visualization of the time, okay, after the water balloon has been catapulted, you can now see what the height would be at that time. Okay, so good points to have when you are modeling and you know you're just in quadrant 1, okay, vertex, y-intercept, and x-intercepts. That's enough to show the whole model of when the water balloon is in the air, okay. So now, that's an A, making the sketch. So now, we're going to do B, okay, and B says, how high off the ground was the water balloon catapulted? Okay, so if you think about this, this was our model we just had. Okay, so it looks something like this. It said, how high off the ground was the water balloon when it was catapulted? If it hasn't been catapulted yet, that means the time is 0. So that's always going to be the y-intercept. So negative 4.9 times 0 squared plus 27 times 0 plus 2.4, that's going to be 2.4 meters. So that is the water balloon's height when it's catapulted, okay? So that's B. Now C says, how long did it take for the water balloon to hit the ground? All right, so if we thought about our model for a second, it was something like this. this was time, okay? When t is 0, okay, it hasn't been launched yet. Now our time, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and here's 6 seconds, right? So how long, let's see, how long did it take for the water balloon to hit the ground? So we have to count from 0 seconds until we hit the ground. So whatever this x-intercept is, that's going to be our answer here. So if you have to solve, right, which we already did before, okay, remember we just solved this, okay, and we got negative 0.087 and we got 5.598. And so for us, this doesn't mean anything, okay, and calculating, we just need to do from 0 until this x-intercept. We don't care about from x-intercept to x-intercept. There are certain problems you have to be very careful, okay? You have to read what it's asking you. I don't need to know about the distance between the x-intercepts here. I just care about, okay, how long does it take to hit the ground? Well, time is 0. How long does it take until h is 0? Okay, when t is 0, how long does it take until h is 0? So that's going to be just in 5.598 seconds. But what you would have to do here, if you didn't already get the x-intercepts like we did, you set it equal to 0, okay, and if the negative one, cross it out, we've got the positive one there. Okay, so that's part C. Part D says, what was the maximum height above the ground reached by the water balloon? Okay, so part D. Maximum height, we know this quadratic looks like this. Maximum height, that's going to be the y coordinate of the vertex. So first you have to get the x coordinate because you are in standard form, right? That's negative b over 2a. And that got us 2.756, right? And then we plug that in. Okay, and that produces an output of 39.594 meters. So the maximum height that the water balloon will reach is 39.594 meters. Okay, so that answers part D. And then part E says, at what time or times is the water balloon 10 meters above the ground? Okay, so if we just think back, you don't have to draw the model every time, but I just want to go over something. Oh, let's make it a little bit more. Okay, it looks something like this. Okay, this was 2.4. This was 39.594. Okay, this was 5.598 seconds, right? TH. So it's saying, at what times will the water balloon be 10 meters above the ground? Well, it starts 2.4 meters, and we know the max height is 39.5. So we know it's going to hit 10 meters twice. Now, if you didn't have a model, okay, you wouldn't know whether the answer is it doesn't hit it at all, it hits it once, or it hits it twice, okay? You just can do the algebra to figure that out, but having a model, like just looking at it helps, but you don't have to do it every time. So I know 10 is about here. So there's 2 times when this is going to hit to be 10 meters. And all we do is we find the times, okay? We have to find the times when the height is 10. So when you know what your output is and you're trying to find the input, when your output is a specific constant value, that is when you are solving an equation. So I need to find the times at which the height is 10. So I have to solve this quadratic equation. Now, you cannot use the quadratic formula until you have your equation set equal to 0. So the first thing I'm going to have to do here is take away 10 from both sides. I get 0 equals negative 4.9 t squared plus 27t, and then 2.4 minus 10 gives us negative 7.6, and now this is what we need to solve. So this is going to give us our times are going to be negative 27 plus or minus the square root of 27 squared minus 4 times negative 4.9 times negative 7.6 all over 2 times negative 4.9. Now we just got to clean this up. So the first thing is we'll get that discriminant value. right? So the discriminant value is 580.04. So what this is telling us, look at the discriminant, it's a positive number. That means we're going to get two real answers. So there will be two times, okay, two real times, and now we just have to see, okay, are they both positive? What's going on with these times? So now we round what we just got as the square root of 580.04. So this is going to give us negative 27 plus or minus 24.084 all over negative 9.8. And now we can find our two t's. Okay, let's do the positive one first and then the negative one. The positive 24.084 and then the negative. So negative 27 plus 24.084 and then divided by negative 9.8 is 0.298. And then negative 27 minus 24.084 divided by negative 9.8 gives you 5.213. So they are both positive. So that means, okay, the fact that they're both positive means your water balloon was launched prior to 10 meters and your maximum height is greater than 10 meters. So you're going to hit it two times. You're going to hit it in 0.298 seconds and again in 5.213 seconds. The height of the water balloon will be 10 meters above the ground. Okay, so that is it for the first application problem, and we will be looking at the next application problem in these notes now.